last time I've been talking about accountability in distributed computing, and well, accountability is a mechanism of detecting misbehaviors and taking the system components, making them responsible for incorrect actions. So if you deviate from the algorithms which you devise for them. And one part of the accountability is fault detection, how to detect misbehavior before you punish the component. And I mentioned a couple of results concerning determining the weakest failure detectors for solving given problems in distributed computing, and also asked me to elaborate on the technical parts of this results, which made me very happy because this was one of the major topics which I started with when I got involved in distributed computing. Actually, that was the topic of my PhD thesis, the weakest failure detector question. And I'm a bit curious because I don't know to which extent you're familiar with the literature and what exactly interests you in this quite exotic topic. It's not that exotic nowadays because we face with the advent of blockchains, we have a lot of protocols in which fault detection is necessary actually, and it becomes maybe so we might come back to these results and maybe find some new results related to different ways of sharing data in a large scale system. But before I begin, so are we familiar with the notion of consensus? Do we know what consensus is? Yes. And so it's, well, we treat consensus here as a problem of reaching an agreement among parties in a distributed system. And one of the major results in distributed computing is that purely asynchronous deterministic consensus is impossible if you have failures. If you just have asynchronous system without bounds on communication, and at least one of the parties can fail by crashing, just simplest type of failure where you just stop taking steps of your own way, then consensus cannot be solved. Okay, so this is the result which we know as FLP impossibility. FLP stands for official Lynchian parties. So this is a result from 1985. It's pretty old. Do we understand what the storage system is with read-write guarantees? Shared file system. Okay. So the other observation which was made some time ago, it's actually dates back to I guess 2000 by Eric Brewer, coined this notion of a cap theorem. So do we know what cap theorem is? Okay, so this is a different phase of impossibility in distributed computing, where you say that certain combination of properties cannot be achieved in the same system, and the combination stands for consistency, C, availability, A, and partition tolerance, B. So this concerns the it's not about consensus. This one is about impossibility of consensus. This one is about sharing data in a large scale. So you have say a shared register to which you want to read and write, and you want to implement it in a way that every client which accesses the shared register, it's not actually physical register, it's actually a replicated collection of copies where you try to write and read. And if these copies are residing on the on a collection of servers, then and you want the clients to be able to complete reads and writes, which means that the system should be available. Yeah, it should always respond to your queries. It should be consistent in the sense that when one client writes a value and the other client later on reads the value, you should read the value. So you cannot lose it. So intuitively, you cannot implement it if the system can get partitioned, because if you want to maintain consistency and availability in one partition and consistency and availability in the other partition, then something would go wrong. Either it's not consistent, in which case you're available but not consistent. You write in one partition, and then the client accesses another partition and reads a stale value. So then you don't have consistency, or one of the clients should block, because it should wait until the partition is recovered before you can read it. So this is I think from 2000, and then it was actually formalized by Gilbert and Leach. They actually brought it down to the implementing a shared register. So these are the major results which we were going to access now. I'm going to study. So first of all, we try to see, okay, consensus is impossible to solve fault tolerant and asynchronous. Let's try to do it with some synchrony assumptions. And we're going to introduce the weakest synchrony assumptions possible, expressed in the form of the weakest failure detector. So we're going to determine the weakest failure detector, the weakest information about failures, which allows us to solve consensus. Then we also observe that, okay, that it also, you can generalize this result, extend this result to implementing a shared register to implement the storage. Basically, an interesting observation here is that the weakest failure detector to implement the storage is the one which exactly fixes partitions in this system. So-called quorum failure detector. So the major literature which I'm going to use is the classical paper by Chandra and Toueg. It's called Unreliable Failure Detectors. It was published in 1996. I will use failure detectors, GACM 96. So this is the paper where they introduced the notion of failure detectors. So abstract oracles, where every process in the distributed system can consult its oracle and get some hints about failures. And then they can exchange this information with each other and then solve some. And then, well, this is just the failure detector abstraction was introduced here. Chandra, Hatzilakis, and Toueg, actually, the paper was published the same year, well, because it was like a tandem of two papers, where they introduced the notion of the weakest failure detector. And we determined the weakest failure detector for consensus. And then I also will use another paper. I think it's Delport. Fauconnier and Garawi, where the weakest failure detector for storage was determined, and combination of these two results gives the weakest failure detector for consensus. So this one was for consensus in the system without partitions, assuming that the majority of processes is correct, and the more general result was obtained here by determining the weakest failure detector for storage. So this is also GACM. I think the journal of the ACM. 2010. Okay. And there was one article which I didn't mention in the list of literature, which the announcement, and this is the it's called the failure detector abstraction, and it's a survey. So it's I think it's decent. So it decently covers the literature. It's ACM surveys, ACM computing surveys. Okay, so that's the goal. So for us, for this meeting, I would like to cover in slightly more technical details how to determine the weakest failure detector for consensus and the weakest failure detector for storage. So here I would show that the weakest failure detector for consensus in the most general case is omega composed with sigma, where omega is the leader election failure detector, which eventually elects one correct process among everybody. And we show that sigma is just the weakest failure detector. Okay, so which is not surprising because consensus is known to be a universal object. So if you can solve consensus, you can implement any sequential object, including register. It's not surprising that consensus requires strictly more information about failures than registers. Okay. Right. So maybe I should define first the failure detectors I mentioned here. So the first thing for us is to maybe define what a failure detector is. So in our model, we have a collection of processes. Yeah, by the way, people who are connected remotely, maybe you can, if something is not clear or is not visible on the whiteboard, just let me know, because I don't have much feedback.
For the moment, I think it's okay. On my screen,
Okay.
I see quite well.
Okay, so we have a collection of processes that communicate through communication channels. Communication channels are asynchronous. Yeah, so there are no bounds on communication delays, but reliable. Reliable in the sense that if one correct process sends a message to another correct process, the message eventually arrives. What is the correct process? A process is correct if it, in an infinite execution, takes infinitely many steps. And it's able to take infinitely many steps, assuming that the algorithm prescribes taking infinitely many steps, which is the case for most of the algorithms we're going to consider. Okay, so correct process communicate reliably. A faulty process just stops taking steps. So we don't consider arbitrary failures here. So there's no Byzantine failures. Byzantine fault model assumes that the process can arbitrarily deviate from its algorithm. Here, we just assume crash failures. Okay, so we usually use notations. We have P1, P2, P3 in this case, 3 processes. Yeah, a distributed algorithm assigns an algorithm to each of these processes, and the algorithm is basically an automaton where you receive an input from an application. Every process has an application, client application, which somehow provides inputs, for example, for consensus. And it has an automaton which changes the state, maintains states. And if it receives a message, it changes the state and sends of messages, a set of messages. We assume that. Okay, so this is the basic model, asynchronous message passing distributed system. Additionally, we assume, given that many interesting problems cannot be solved without any synchrony assumptions, we assume that there are some oracles here, like we call FG1, FG2. These are failure detector oracles. So every process can also consult its failure detector oracles. It's like a local failure detector module. It's another algorithm basically, which essentially what happens behind this interface of the failure detector is that it sends queries and waits for responses, and it encodes all these timeouts which you can expect in the real system. And based on this exchange, it produces some information about failures. What's important is this failure detector modules, they only depend on failure pattern. Basically, it depends on the actual times when processes fail. Yeah. And the outputs only depend on this. They don't depend on the algorithm which this process runs. So formally, we can say that a failure detector, let's call it D, is a map between a failure pattern to some range of failures. So a failure pattern is a map which maps the range of times, like these time moments, to sets of processes. Yeah, I would say the pi is a set of processes. In this case, P1, P. This is a set of processes. Time range is just let's take discrete time.
So just correct me if I'm wrong. So potentially, for example, FD3 knows the stuff about the failures of P1, P2, failures of everybody, and okay.
Yeah. So
but only about their failures, not about their.
Not only about the failures. Yeah. So it basically says who's faulty, who's not. May say who's faulty, who's not. The one example of failure detector is what we call a perfect failure detector. Failure detector usually called P, and it's it's accurate in the sense that for all times and for all processes P, the output of PT is a subset of f of t. Yeah. So this is the faulty process at moment t. This is the output of failure detector at moment of time t and at process t. So it always, whenever it suspects someone, it's faulty. Yeah. And then it says that for all p correct, yeah, for all correct process which never appears in this faulty which never appears in the failed pattern. So it's for all correct process. Yeah, I'll just denote it this way: correct with f. It exists, and for all q faulty of f, and there exists t such that for all t prime more than t, q is in f, sorry, in p of pt prime. So from some point on, you always suspect a faulty value. So you detect every failure, and every failure is correctly detected. So this is what we understand as a perfect failure. So this is just one example, and maybe I should now define what we mean by this omega and sigma more formally. Perfect failure detector is exactly, yes, it's very, very strong in the sense that it requires basically a synchronous system to be implemented. Because you need to, basically what it means that you know exactly how long it takes for a process to respond to your query, and if you don't receive response, you know that the guy is faulty. That's how you detect failures. Right. So let me try to define.
Just to try to understand this is by queries only, right? That these failure detectors work. They have no further knowledge on the state of the processor, do they?
Well, you can see it as a query. But later on, I will just assume that it's like a monitor. It always outputs something. Yeah, you can check. It's like your local variable. You can read from time to time and see what's there.
But so I thought the channels were asynchronous, right?
Yeah.
So without bounds on the delay of,
yeah.
And so this works also for the channel between the
this is technically it's the same machine.
Okay.
Yeah.
So here it's in a sense synchronous, or
you can see it as a synchronous. Yeah, you can instantaneously. You can just.
It's inside the box.
Yeah.
It's inside the box.
It's inside the yeah. Whenever you devise an algorithm which uses failure detector, in the algorithm you can say query local failure detector. So you have an additional step in your algorithm which can.
Okay. So at least for the processor they are associated to, there is no like delay of detection of. But FD2 is only in charge of detecting failures in P2 or more.
No, or more. No, of course, it actually for P2 it's interesting who's faulty around. So the implementation of these oracles typically involves communication between them through the channel, yeah.
Through the links between
the process. Yeah.
Okay, so it's instantaneous for FDI as instantaneous detection capability on PI.
Yeah.
But so if there is a failure on P1. It will detect it to the best at the speed or with the delay of the communication between P1 and P2.
For example, yeah. But I think the innovation of this abstraction was that actually, and it's coming in the title. The first article on this was called Unreliable failure detectors. So they would say that even failure detectors which make mistakes are useful, because this one doesn't make mistakes. It's perfect. But in fact, if you have a failure detector which sometimes suspects someone erroneously and then says, "Oh no, sorry, I was mistaken. The guy is actually correct," and then suspects him again and again, so even this kind of failure detectors may be useful. And one of the failure detectors of this kind I'm going to define now. It's called omega, the eventual leader election failure detector, and it only provides guarantees which hold after some time. And you don't know when it holds, when it's going to hold. So it's sometime we should have no idea when it actually starts faulting. But even this kind of unreliable failure detector is very useful for solving some problems, in particular consensus. So this omega is the eventual leader election. So the range of omega will denote R. Omega is just P, pi. So it just outputs a process ID every moment of time. At each moment of time, at every process, just outputs one single process ID. And guarantees that that there is a time in any execution. There is a time t, such that for all t prime more than t and all p incorrect of f, or where f is failure parameter for which we define this, and there exists. Well, maybe I should differently. There exists q incorrect of f and the moment of time such that yeah, this omega p equals from some point on, everybody agrees on the same correctly. But before, and since we don't know when this moment of time t arrives, yeah, no moment of time, a process can be sure that the output of this failure detector is actually correct in the sense that it corresponds to the output of everybody else, and the process is correct. So it only guarantees that from some point on, we stabilize on the same correct leader, but before this unknown a priori moment of time, it may fluctuate. So this is what we understand as omega, and we're going to show that first of all, we're going to show that omega is necessary for consensus. Yeah, any algorithm which solves consensus using a failure detector can be transformed in the algorithm implementing omega. And we're also going to show that there's another necessary failure detector for consensus, which is called sigma, quorum failure detector.
So in the existence of Q, is it clear that there is uniqueness? You say leader election, it seems it's only one.
Yeah, from some point on, there's exactly one. So there exists Q and T such that for all times up to more than T and for all correct processes, they all agree on Q.
But why does it imply uniqueness of Q? Is it clear?
Well, because I say for all correct processes, every correct process agrees that this guy is.
But I understand.
But before this moment of time T,
there could be a Q prime where everybody also agrees on Q prime. No, no, because
after max of
max,
T prime related to Q and
there is a Q, and therefore okay,
and T prime related to Q
yeah,
prime.
it's just the logic implies that it's okay, it's uniquely defined. Okay.
Eventually unanimous. So
on Q,
you don't have much choice.
there exists a Q such that, and since the
okay, so for the quorum is a subset of processes. Typically, a quorum in distributed computing literature, a quorum is a set of processes who you consult before you complete your operation, and you need somehow affect the states of a quorum of processes before you say that the operation is complete. And, as usual, in this quorum, like if you think what quorum is, yes, in the parliament you need a quorum to pass a law. And here it's a similar logic. So the range of this quorum failure detector is a set of subsets. And there are two properties. One is that for all P and Q and all times T and T prime, the output of sigma P at time T and output of sigma Q at T prime should intersect. whenever I query my quorum failure detector, what I get should overlap with the result of query or failure detector anywhere at any time. Okay, so it's a strong
seems very extremely strong.
Yeah, but we're going to show that it is necessary, and in a way, this is something which precludes partitions, because as long as you are not completing your operation before you hear from a quorum, you guarantee that someone else who also does the same will hear at least from one of the processes from whom I heard. Okay, and well, but by itself, it's not probably sufficient, because to query a quorum, you need to make sure that the quorum responds. So you need to guarantee that for all P incorrect of F, now all these definitions assume that for a fixed failure pattern F, or a fixed timing of failures, there exists a time T such that for all T prime more than T, the output of P at T prime is correct. It contains only correct processes. Yeah, from some point on, whatever my quorum failure detector tells me, says, look, this is a quorum, but it should only contain correct processes from some point on. Okay, so the idea, roughly, if you want to use it in an algorithm, you issue a query, and then you wait until the currently detected quorum, according to my failure detector, responds. Yeah, every member of this quorum sends me a response to my query. So this is okay. So this is about safety. This is more about liveness. Yeah. So the query to a quorum would eventually terminate. This one would guarantee that every two quorums. Okay. Are we together?
Totally.
Okay. Cool.
So the system may eventually completely fail, but you don't care, right? So if, for instance, because the first condition is only for those which are not failed, right? So if everything fails, then the condition is trivially satisfied, right? So you don't guarantee the system will work, but if it will work, it will elect a leader and detect and identify according to second condition the default P1s and okay.
Yeah. So one way to think about it is to say, assume that you have a system in which you guarantee that a majority of processes are always correct. Some majority is correct. N processes and at most n minus f minus 1 processes, n over 2 minus 1 processes are false. So in this case, I can trivially implement this failure detector just by saying, defining this quorum to be the set of processes who respond to my query, and then that would be a majority. Every two majorities overlap, and eventually only correct processes will respond. But the crux here is to show that even if you don't have this, you don't have a majority, because failures are not necessarily distributed equally. And there are some components which are more likely to fail, some components which are less likely to fail. So this is a more general abstraction, which allows you to capture systems beyond this majority. Okay,
What is not clear for me is about the failure. If a process fails, later can it be okay again and then
no. We assume we don't assume any recoveries. Yeah,
okay,
you can, but not in this case. No, either it takes steps forever, or it stops taking steps and never comes. Okay, so the crash recovery model is an interesting topic, and actually now it becomes. Now it becomes with this non-volatile memory. It becomes very important, because sometimes you can store your state in a stable memory, and even if your machine crashes, you can recover the state from the memory. But this is not what the classical failure detector literature assumes.
In fact, in this model, this would simply be considered as a correct process. A machine which would do that.
But then of course the challenge is what exactly you store from it. Okay. So yeah, this we don't need.
But then I do not understand the first condition. You have
For this one.
This one, yeah.
Huh?
If a process fail and then it fail any time after, this will be always true, in fact, because what you need is just a process that do not fail any time.
No. Here it's important that even P queries its failure detector and none fails. It's important that the output at the moment before it failed still, because this is in this. If you think about it, it's like the guy could actually use this failure detector output to do something, like for example, to write a value in the memory, provide the output to its application saying, okay, I completed this write, and then fail. So that you still want this complete operation to be consistent with respect to some high-level guarantees. Yeah, but maybe technically speaking, I should probably say that for all P, Q, T prime, such that P is not an f of T and Q is not an f of T prime, meaning that they are not. What I mean here is something which they see before they crash. But, okay. Right. So now it's gonna be a bit. I don't know. You stop me if it gets a little bit unclear, because I basically squeeze a paper which contains like 50 something pages in half an hour presentation, so it's going to be a little bit tough. So this is the result of showing that, yeah, the result which shows that whenever you have a failure detector which enables solutions to consensus in this model, then this failure detector can be reduced to omega. Yeah, so omega is at least as strong as this failure detector. So for this, I need to introduce the notion of a reduction between failure detectors. So failure detectors are these functions, yeah, as I defined it, and they have some partial order. Yeah, some of them are incomparable, meaning that you cannot implement one into another. But some of them are comparable, and you can say that one is stronger than the other. So you can say that failure detector G is stronger. That's the definition that I think. Then failure detector G prime if for all failure partons there exists there exists an algorithm A G to G prime such that for all failure partons it's G to G prime, yes, that by collecting the inputs of D, it can emulate the output of G prime. So it can produce, yes. I'm not going to really go into detail in this definition, but intuitively, it's like I query failure detectors modules of D, exchange information, and at every process, I simulate, like I have a local variable which stores the output of D prime, and this output satisfies the specification of D prime. That uses D to emulate. This is so. Then you can say that they are equivalent, and one is stronger than the other, and vice versa. Okay, so this is one thing, and then we can say that D is the weakest failure detector. I just write it this way. Actually, in the literature, sometimes we write a weakest failure detector because they can find multiple weakest failure detector for a given problem, which are all equivalent, but they have different formulations. For a given problem, PV, I will try it for PV. If, first of all, PV can be solved using information provided by D, and for all G prime such that PV can be solved using D prime. Yeah, we can have, I'll just write it this way. G is stronger than D prime. That's how we write. G stronger. No, sorry, weaker than D prime. this time. It's the weakest. Yeah, so you can always, whatever failure detector I take, I can solve the problem using this failure detector, and I can simulate.
And is it obvious that all the weakest failure detectors are in the same equivalence class?
Well, for this reason, yeah, because all of them allow to solve the problem, so you can transform one into another.
Okay.
Yeah. There's another question whether the weakest failure detector exists. Yeah, this we a priori we don't know. Yeah, maybe it doesn't exist. Maybe you can always find smaller and smaller and smaller and smaller, but they never converge. And there is a result which shows that for reasonable model, it always exists. There's always the weakest failure detector for whatever problem.
Yeah, more generally speaking, I was wondering if the partial order on detectors is in fact a lattice or.
Yeah, so in this case, it is. You can show that it's what you call semi-lattice. So there's always
Okay, yeah, just minimal.
Right. Yeah. So basically, this result about the existence of the weakest failure detector is shown. It shows that it's a lattice in the sense that for every pair of failure detectors, always a weaker one, which is weaker than both of them. Yeah. So this partial order is a lattice order. Okay. Right. So this is what we are looking for. So the theorem we're going to prove is the first one is omega is necessary, meaning that it's weaker than any failure detector that solves consensus. Yeah. So this is this means it's D is sufficient. This means it's D is necessary. So now we're going to show that omega is necessary. Sufficiency I'm not going to discuss because it's a classical protocol. Actually, it's what we know is Paxos protocol. It shows that omega is necessary. The Paxos protocol of Lamport solves consensus, assuming that there is an eventual leader election. So the core of the Paxos paper. You know, are you familiar with the Paxos? Okay, so in this consensus literature, and actually in blockchain literature nowadays, there's one fundamental result showing that in an unreliable message passing system, you can solve consensus, assuming a majority of correct processes, which we're gonna fix later, in a so-called abstraction-free manner, meaning that if there is a single process which keeps proposing values from some point on, eventually it will decide on the value. If you constantly have contention, then it's hard to do, and it's technically impossible. FLP shows that it's impossible. But if you have in addition to this protocol, you have a leader election oracle, then you just let the leader always propose values, and from some point on, there is a single leader who will keep proposing value, and the value will be decided. So this is, in a nutshell, Paxos protocol. And yeah, and then it turns out that you can abstract away the majority assumption using sigma, and then it shows that omega times sigma, composition of omega and sigma, allows us to solve consensus. From this point on, I'm not going to talk about sufficiency part of this results. I'm only talking about necessity. Because sufficiency has been known for quite some time. Necessity is, yeah, so the first result was Chandra, Hadzelak's and Toueg 96, and then the second one was basically 2010. So it's not that old. Oh, pretty old. So. Okay. Omega is necessary to solve consensus. How we prove this kind of things? So basically, what the guys. So this is the paper which I call CHT, Chandra, Hadzelak's and Toueg 96. So what they did is they opened the box of the FLP impossibility. So they would say, okay, let's look why consensus is impossible, and let's see how we can actually add some extra information to this impossibility result to make things possible. And here I need to introduce some definitions. And first of all, we say, okay, let D be a failure detector that solves consensus. So our goal is to show that omega is weaker than D. D is stronger than 1. That's our goal. Right. So a little bit of formalism. So what do we mean by an algorithm now? Okay, the algorithm proceeds in steps. What is a step of an algorithm? Or what is an execution of an algorithm? An execution is a sequence of steps, and the steps in our case will be so an execution. An execution is a sequence of steps, and a step is a tuple. Every step, it's a distributed system, so you give every step is taking place at some process. Yeah, so the process identifier. It has a message which the process receives in this step, and because it's an exchange of messages. So the main trigger for a process to take a step is to receive a message. Yeah. And additionally, since it's a failure detector based algorithm, you have a value coming from a failure detector. So you have 3 identifiers in a step. Yeah, so process P receives message D, and when it queries a failure detector, receives value D. And in fact, you can see, I don't know, the PI2, MI2, DI2, etc. So you can see this as an execution. Here it's a consensus, so I simplify a little bit. I assume that the inputs are predefined. So every process has initially, in its initial state, the input. And there are some initial configuration which assigns inputs to the process. So then any execution of the algorithm can be represented in this form, where some scheduler decides who takes steps at what point, and says, okay, oh, PI1 takes a step, receives the message MI1, and sees the value DI1 from the failure detector module. The message could be empty. For example, there are no messages in the message buffer destined to PI1. In this case, it's just empty. Now we have 2 assumptions about these executions to say that the execution is valid. If the execution is infinite, then every correct process should take infinitely many steps. Yeah, and correct process is correct with respect to the failure pattern, which we consider in this model, because the failure detector output depends on the failure pattern. So the execution is this what we call a schedule plus failure pattern and plus the input configuration. There are three things which identify an execution. So this is a schedule of steps, a failure pattern in which the steps take place, and the input configuration. And the sequence of steps should satisfy the property that every correct process takes infinite many steps, and every message sent to a correct process is eventually received. Yes.
So the MI are the input. We don't care about the output. We don't write them down. They exist somewhere, but they are not interested.
Yeah, here we use the assumption that the algorithm is deterministic, meaning that it's a deterministic automaton. If you have a state, you receive a message and the output of failure detector. There is only one state transition you can take, and only one message. Well, only some strictly defined set of messages which you send in the step. And then, of course, there are other assumptions saying that okay, every message which you receive here should have been produced previously by another process. So it's so there are some restrictions, but roughly we treat an execution in this form. Yeah, so the sequence of steps. And basically, what we're going to play with is to show that okay, by using this sequence of steps, I can actually emulate this thing. Yeah, so whatever, and I am going to use the fact that this set of executions in every such execution consensus is solved. Yeah, so and the algorithm is based on simulation. Yeah, what I'm going to do is I'm going to run 2 parallel tasks at every process. And this is I'm going to describe this algorithm, which reduces d to omega. It runs a communication task, which basically means that every process queries its failure detector module, sends these values to everybody, collects values received from everybody, builds some form of structure, which is a directed acyclic graph, and then uses, so this is a communication task, And then there's a computation task which uses this directed acyclic graph to simulate a number of runs of this algorithm. Yeah, there's an algorithm. Yeah, so using algorithm A. Yeah, so I simulate this algorithm A locally. So I collected all this information about failures, which other processes told me, and my failure detector module told me. I built some structure. On this structure, I use it as a stimuli for producing subset of executions of the algorithm of this kind. Then I look at the outputs of those executions, my locally simulated executions, and I get some hints about how to produce, how to electrolate. And then the beauty of this algorithm is that up from some point on, I converge to the same output everywhere. So I put exactly the same leader everywhere. So it's based on locally simulating the runs of A. The algorithm which uses D, the abstract rate detector. So basically, it's funny because the algorithm doesn't assume that you know what this D is. The only information I know about D is that D solves consensus, and there is this algorithm A, and I use this algorithm as a parameter of the simulation. Okay, and this is the major technique. So it's always used in this weakest failure detector results, where you just locally simulate the whole system. Every process locally simulates the whole system, looks at the outcomes of the simulation, and draws some conclusions. Okay. So I mentioned FLP. So I'm going to give some small hints about what this FLP was about, but generally what the impossibility of consensus was using was the fact that you can sort of foresee the future. You can take all executions of your algorithm, and you can see that, okay, there's always an uncertainty. You cannot, in no moment of time, in a finite period of finite time, you can actually determine what is the decision value. So there's always an execution in which you never you are never able to determine what is the possible outcome. And consensus, you cannot have this luxury. You can in every execution you should eventually decide. You decide on 0, you decide on 1, where 0 and 1 are two possible inputs. But in fact, that this is asynchronous. There's always this uncertainty in some executions. And in this, how they construct this execution, they would say, look, let's consider a reachable configuration of a given algorithm. Yeah, let's say this is an algorithm. We reach some configuration, meaning that there's a finite execution which ends up in this particular state. So this is, I use this notion of a configuration. So it's we say that it's if there's an extension of this configuration, such that in one extension, one sequence of steps which extends, you decide 0. Okay, and well, I just say 0 at the moment, yeah. And there is another extension in which you decide 1, yeah. And this is inevitable in consensus algorithms, where depending on in which order processes take steps from the same state, you can decide 0 and 1 or 1. Then we say that it's valid. Typically, the valency of an algorithm determines the decisions taken in extensions of a given configuration. Valency of configuration, sorry. So this is so if the configuration is not bivalent, yes, it can be. Then it's called univalent, which means it's either 0 valent or 1 valent. Meaning that if there is an extension of the algorithm in which the value is decided, it's 0. Then say this is a 0 valent. If in every extension, if there is an extension of this configuration and the decision is 1, then it's 1 valent. Okay, so the uncertainty is gone. So if you reach a configuration in which only possible decision from this point on is 0 or 1. It's a univalent configuration. And intuitively, when we solve consensus, we want to reach a univalent configuration as fast as possible. Okay. So there's two configurations, and here we talk about the scope of all possible configurations reachable by executions of this protocol. Okay. And this is something which we're going to use in these local simulations. Okay, so right, so this is one thing. Do I need anything else? I think it's good for the moment. So let me describe this communication task in more detail. So I build what is a communication task is doing? I query my failure detector. I'm as a process. I query my failure detector. I add some sequence number to it. It means okay, this is my kth query, and I send this to everyone. I collect this type of messages from other processes, and I build a graph. How I build a graph? I build a vertex as a query of a given process at a given moment of time. And an edge is the causal relation between these two. If I query my failure detector, I send it to someone, and then someone received this message and then queried its failure detector, then this other second vertex succeeds the first. And there's a causality. And so sometimes we use this kind of diagrams. So you have P and Q. So P queries its failure detector, and let's say it's P D K. So this is the value. D is the outcome of failure detector. K is the sequence number. Then it sends it to process Q, and then this process Q queries, and it's Q D prime K prime. Yeah. After having received this message, then of course this precedes this event. Yeah, because we assume this natural happened before relation. So which means that in the corresponding graph of Q, you have an edge of this kind between these two tuples, P dk and P or Q G prime K. So essentially, what you do is you, instead of what maybe I should refine a little bit, you're not only sending your the result of your query, you send the whole graph. And then by doing this, you have growing graphs everywhere with this causality relations. And roughly speaking, all these graphs converge to the same graph at every correct process. It's infinitely growing. It's all constantly growing. Yeah. But you can be sure that whatever a correct process sees at its graph, it's going to be subgraph of any graph for every other correct process from some point. So it's constantly growing information about in which order some processes query their failure detectors. But it's only a DAG. It's a directly acyclic graph, because you can always have some process querying their failure detector modules in parallel, and they are not causally related. So of course they have some queries which succeed, both of them, but they are themselves they're not ordered. It's a DAG. You don't have cycles because again it's time, so you cannot have me preceding some events and someone else, and then he preceding my events. So we don't have cycles of time, so that's why we have no cycles. Okay. So this is DAG. So for every process PI, it maintains some DAG GI locally, which grows. It's a dynamically growing abstraction. And we guarantee that, yeah, well, as I said, they sort of converge to the same graph from some point. Okay. So, yeah.
What does graph convergence?
Yeah, that's not precise. Yeah. It's what I mean is that yeah, maybe I should write. Yeah. So for all P and Q incorrect, F fix this failure part in F, and for all T, there exists T prime such that G I of P is a subset of G J of Q. G P of T is a subset of G Q of T prime. Right. So now I'm going to basically use this DAGs. What is a DAG? It's a graph with paths. Yeah, and this paths have no cycles. So it's basically this path in the graph shows that okay, P queried failure detector at some moment got the value G, Q got value G prime, then R to value G double prime, and so on. So you have this sequence of steps. Essentially, well, it's almost sequence of steps. Basically, it's almost sequence of steps, except that we don't specify the messages. It's just P, G, PI, and so on, which could have taken place in reality, because this is the distributed system that could have been observed in this particular order. And we're going to use this sequence of failure detector outputs to simulate an execution. Actually, we're going to use it to simulate a number of executions, all possible executions which we can allow to simulate. Let me this one.
So here it is crucial that the channels are with arbitrary delays, but transmit the right information without errors, right?
Otherwise, the channels are reliable. Yeah, I didn't say this, but yeah, they don't corrupt messages.
Because otherwise you could not be sure to build the same history of graphs.
Of course, yeah. Channels are reliable, they don't corrupt, don't duplicate. Yeah, so. Okay. Right. So now I can use a path. So I'm jumping a little bit, but what I'm saying, we use the path. I mean, a process in this reduction algorithm. The process uses a path in its graph, locally constructed, to simulate a set of executions of the algorithm A. Yeah, use a path in GI to simulate, or maybe a path, all the paths to simulate runs of A. Given some initial configuration I, some. So we actually explore a set of possible initial configurations. Here we talk about binary consensus. So here, which means that we can consider all possible distributions of zeros and ones to all processes. So for any fixed distribution of inputs, we can simulate a run. It's a number of runs. Okay, how do we do this? Well, basically, what we do is we just well, should I say? Actually, whenever I say a graph, a DAG, I take the transitive closure of it also. Yeah, if event E precedes event E prime and E prime precedes E double prime, E precedes E prime, so E double prime. So it's and I use as a path. So all possible paths. It's not about computational complexity here, so it's an enormous task, but for the sake of the argument, we just do this. Right.
One question. I mean, this records the history of what has happened. Why are there? I understand it builds this graph, but it collects only one execution, right? So why are there?
Well, imagine that you have also here process R, which also queries R, whatever, D double prime, K double prime, and this message is received here. So what happens here is that you have this path here in the graph, you have this path here in the graph. You can what you can do is to simulate a run in which R was first to take a step and it saw the output G double prime, and then Q took a step and saw G prime. Or you can simulate a run in which P was first and then. Okay. So you go along this path and you treat this as two steps of your execution. Or you go along this, you treat this as two steps.
I see. So the knowledge that you have accumulated is not enough to have full vision of what has happened in full order, right? You have
of course. Yeah, that's the artifact of any distributed system, well, especially asynchronous, that you don't have any knowledge of the steps taking place concurrently. So you have multiple ways of ordering that. Yeah, so you can simply ignore this to say, okay, this starts from here. It's also possible. And so you have multiple possible interpretations of this failure detector outputs. And then you assume that all these processes, they start with the specific inputs. And then according to these inputs, the first message is always clear what they send, because the algorithm tells, okay, given the input 0, I send this message to everyone, for example. And then you proceed along this path in GI. And I take all possible paths and I simulate a tree. It's actually what I get is a tree now, because it's a set of paths. Every path is in execution. And then starting from I have the initial state, and then I have basically one execution here, one execution here. Here you can probably have deviations and so on. So this gives us a tree, an execution tree. Here we're actually going to come back to this balance things, because this is where I can actually apply tree. I think they used this epsilon kind of thing. So there's some, so for any input configuration you have a corresponding tree. So basically what you have is a forest of locally simulated trees. Everybody has this set of, maybe I shouldn't use the same index, because I is the process identifier, so I have IG. Okay, so you have a graph. I use graph to simulate runs. I get a tree, basically a tree for every input configuration. Basically, it gives a forest, a set of trees. And now I can come back to balances. I can say, okay, look, what's going on with these balances. And here, yeah, I guess, I don't know how much time we have. We actually
we're almost finished.
Almost finished. Ouch. Okay, so that was probably a futile attempt to cover this. Okay, let me.
Better to do less things and to
I agree.
understand really what's going on.
I agree. Okay, let's zoom a little bit on this. I guess I will be able to do it in 10 minutes. This is a tree. Every path in a tree is an execution of a given algorithm. In some of this execution, this is a consensus algorithm. And the consensus algorithm is supposed to produce decision values. Yeah. In some of these executions, you have some processes deciding. So you can locally say, okay, look, this guy received this messages. The guy should reset. So I can see, okay, there is some decision here. Maybe I use a different color. There is decision at 0 somewhere here. Some process here decided 1 maybe. What I guarantee, since we assume that the algorithm is correct, what we know for sure is that in a given execution, you don't have different decisions, and because it's consensus. But in different executions, you can have different decisions, and we are particularly interested in executions where different decisions are taken in a very decisive manner. Like from some point on, depending on the step of a given process, you have different decisions. And this is exactly what we're going to zoom on. We're going to look for a specific sub tree in this tree in which you have like fixed decisions coming from a given process. And this is the process which is we're going to suggest as a leader. So let's see. So we are looking for a specific, it's called the decision gadget. I don't know, they called it decision gadget. It's a subset of this tree, such that, well, you have some configuration here, and you have 2 steps of the same process. This is one. There are 2 types of decision gadgets. This is the first one. P, M, G, and P, M, G prime. I think this is how they defined it. So the process receives the same message, but it gets different hints from the failure detector. Yeah. It is possible, yeah, because again, in this construction of a graph, I can take either this particular step of the guy or some other step of the guy extending the given configuration. And if it turns out that after this guy taking a step, the decision is 0, well, more precisely, it's 0 valent, and this is 1 valent. Meaning that in this particular simulation, every extension of this configuration brings decision 0 every in my local simulation, not because the simulation is finite. I only have finitely many steps here. And if I apply this step, I have one value. This is what we call a fork. Yeah, it's because you have sort of this decision depends on who takes a step, and actually in particular it depends which step P takes here applied to this particular configurations. This is one. It's one specific type of this tree. Okay, nothing, not more than that. And we're actually going to show that this you will end up by locating this. It must exist. A different type of the tree. One of the two kinds should exist, and the second type is let me go here. Is what we call a hook. So it's very similar, but except that now it depends on two processes. So here we have the different kinds, also C. By the way, since you have these two outcomes, the original configuration, initial configuration IG here is bivalent. Okay, so here you have P taking step with some fixed step. Then you have Q taking some mirror D here, and then P applies the very same step. Okay, so I can either apply it directly to C, I can wait until Q moves and then apply it after the move. And again, I require that this is 0 variant and this is 1 variant. Okay, so this is what we call a hook. So the most, like the crux of this proof is to show that in every simulation, you eventually end up on locating a fork and a hook which remains stable. Stable is important here because it's a finite structure. At any moment of time, at every process, the simulated tree is finite because I only collected finitely many outcomes of feeling. But it's constantly growing. It's constantly growing, and I guarantee that there is some fork or hook which stops staying there. It will never move. Yes.
So I'm anticipating that you are going to tell us that C is going to be a great leader or something like that.
P is going to be the leader.
P, sorry.
Yeah.
It's going to
And
be
Q here. Yeah.
All right. But we don't have only one tree, we have a forest, right?
Right.
So what if the other trees disagree?
So there is uncertainty. You have multiple. Well, I'm going to say that these forks and hooks exist first. And then I'm going to argue that since the tree, actually this forest, contains countable vertices, I can actually map it to a natural order. It's countable in the sense that because I'm going to use the sequence numbers, which I don't put here, but intuitively you can make total order on all these vertices. It's growing, but it's totally ordered. So I can find the first one. Yeah. So I find the first one, right? And I find the first hook or fork which I locate in all these trees. And since I'm using the assumption, the fact that these trees are converge to the same infinite tree in a way. Eventually, you will stabilize on the same fork or hook, and the hook and the guy who is moving here or there is going to be the leader. Why it is a leader? Maybe because we're already short in time, I sort of skipped all the steps. But why this guy is a leader? Why it is correct? No. Why it is correct? Because the agreement is there. We all agree on the same fork or hook. We locate the same guy who is taking important steps in this fork or hook. And then why do we know that this guy is correct? Imagine it's not correct. Okay, so for example, here, if Q is faulty, it means that it stops taking steps after some moment of time, which means that there is an extension here in my DAG in which this guy doesn't take steps. So I can apply this extension. So suppose Q is faulty. From some point on, it takes no steps, which means that there is an infinite execution of steps which do not involve Q. And then I apply this execution E here to this particular vertex here. And I should decide at some point, some process should decide, and the decision should be 0 because this is 0 value. Okay. But since P what is the difference between this state and this one? The only difference between these two steps is the local state of Q. Should be careful here. Q might have sent some messages at this step, but since the communication is asynchronous, I can delay all these messages until 0 is decided. So here I apply the very same sequence of steps. And actually, I should delay it here because this is where Q actually moved. I delay all this, and I can apply exactly the same sequence of steps and decide 0, which violates the premise that this is a one-byte configuration. Similarly here with the fork, it's even easier because here the only difference between these two is again state of P. I apply the same execution in which P. So here it's Q free. I say it. So I apply the same E here. It's also inside 0. Here again, I apply P free execution. The very same is applied here. I decide 0 here. I should decide 0 here, which violates the assumption that this is a decision. This is a fork. So that's it. That's it concerning omega. So okay, so this is one part which probably was a breakthrough in this literature because they not only defined the notion, they also provided the formalism of how to reason about weakest failure detector. So the part about sigma I didn't have time to measure to describe. So I don't know if you want, we can do it for maybe some other time, or otherwise I could also encourage you to look at the survey. The survey actually we tried to give in general how to, from the systems perspective, how to implement failure detectors, and also this theoretical computability benchmarks side of failure detectors, where given a problem, we characterize precisely the synchrony assumptions which enable solutions to this problem, necessary and sufficient conditions, which makes it kind of interesting from the theoretical viewpoint. However, this is not very practical in the sense that this kind of reductions are very, very expensive. Yeah, but on the other hand, you can show that, okay, at least theoretically, if you have a system in which omega cannot be implemented, consensus can be solved. That's maybe one of the things you can learn from this. Questions?
Any questions on the bridge or in the room?
So I'm puzzled by the fact that if everybody fails at step 1, everything is perfect. And so is there like a quantitative theory where if you put, say, some randomness, like in reliability at the time at which things fail, you learn what is the proportion of time under the lifetime of the system, maybe before this time where everybody is dead, where the system has detected is working properly, maybe has elected this leader, which is not the empty set. Is there you cannot complement that by something quantitative on when these statements are non-empty? I call empty the puzzling fact that when everybody has failed, the conditions are satisfied, right? So you could put, say, exponential times on the time to failure, or even you could say that some do not fail, never fail, right? And you would like to see to say something more on the system, which is the say from what time on typically, or for the proportion of time in the first case, you really detect the leader when the system is not dead.
Right.
Does it make sense? Or?
Well, not in this formalism, because here we avoided making any assumptions about time. We don't say anything about how long it takes for a process to fail, how long it takes to take a step, and how long it takes to convey a message. The only assumption I made about executions is that if you're correct, you take infinitely often. These steps appear infinitely often, but it can appear 1 in a million times. So it's so I guess if you want to make any assumption, any conclusions about the time to elect a leader, you need to make assumptions about the scheduler. example, yeah, and that's yeah, you can do this. So there are some interesting, not so many. I don't think people worked on this a lot, but there are some papers where they take this what they call stochastic scheduler, where they say that every process is there's this fixed probability of a process of given process take a given step, a given time slot, and then they give naturally they provide probability bounds for reaching different properties in different executions. So that exists, but yeah, I don't know. I don't have much to say about it.